Hello, I'm Naoki from Tokyo University of Agriculture and Technology. Today, I talk about our work, computational design of polyomino puzzles. Puzzles have fascinated people all over the world for centuries, and therefore, there is plenty of puzzles. These puzzles shown on the slide is a portion of puzzles I played in the puzzle event. I enjoyed solving puzzles, and there were many people from kids to adults who enjoyed solving puzzles as well. While some puzzles can be solved easily, the other puzzles are difficult for me. Interestingly, which puzzles are difficult is different from person to person. This is because solving puzzles require both logical thinking and inspiration. So, it is difficult to find puzzles with a moderate level of difficulty to me or to someone. Hanayama is one of the famous puzzle makers and provides indicators of the level of difficulty for each puzzle in their puzzle catalog. The upper left one has level 1, which indicates the easiest, and on the right page, there are more difficult puzzles, such as the one I annotated with a rectangle, which has the maximum level of difficulty. These indicators, however, are not always true. For example, I solved the level 6 puzzle with the orange rectangle within 10 minutes. However, the bottom left puzzle, annotated by the blue rectangle, is level 4, which I have not solved for a long time. While we can buy off-the-shelf puzzles at the store, designing new puzzles is a complex and difficult task for both novice and sophisticated puzzle designers. So, it is difficult for users to design their own puzzles by themselves. Puzzle design software, such as bar tools, can be used for trial and errors when designing geometric puzzles. Although these tools help users designing valid puzzles, here, valid means a puzzle that can be assembled and disassembled physically. The designing process is still intricate and difficult even for sophisticated puzzle designers, as well as novice designers. In this work, we propose a computational design tool for designing geometric puzzles. We focus on geometric puzzles with polyomino-like shapes. Users can design their puzzles interactively. This is achieved by the proposed top-down partitioning-based algorithm. We employ a capacity-constraint graph partitioning or CCGP algorithm. It is simple, general, and scalable. So, we can apply CCGP not only to 2D polyomino puzzles, but also to 3D polycube puzzles with minimal modifications. Several techniques for designing geometric puzzles have been proposed. Wall et al. Proposed 3D polyomino puzzles. Input 3D models are decomposed into polyomino pieces. Song et al. Proposed recursive interlocking puzzles. The resulting puzzles ensure recursive interlocking when assembling and disassembling, which means there must be a unique solution. Or, there are puzzles that can be transformed from one shape into the other shape. Such puzzles are called dissection puzzles. Most of the previous techniques employ bottom-up constructive approaches, and the puzzle generation process is automated. Therefore, it is difficult to control puzzle piece shapes as user's intention. Thus, we propose a top-down, partitioning-based approach that allows users to control piece shapes to some extent. The overview of the proposed approach is as follows. The input to our tool is a 2D shape or 3D models that define target regions. Other user specifications, such as the number of pieces, are also provided. The output of the tool is fabrication-ready puzzle pieces. For 2D input, the output is a vector graphics of the partitioned shapes. For 3D input, the output is a set of 3D models with STL file format. The puzzle piece generation is described at the bottom of the slide. Given an input region, we first try to tile polyominoes. Then, we construct a tile graph and apply the CCGP algorithm on the graph. Finally, we obtain the puzzle pieces from the resulting partitioning. So at the first stage, we perform base tiling. Given a target region and base tile set, we compute its tiling on the target region. Such a tiling problem is known as the exact cover problem, and we can formulate this problem as an integer programming. Note that if we can't place base tiles to exactly cover the entire region, we can use another base tile to exact cover. For example, we can always exact cover of the region by using monominoes. The monomino is a 1x1 size polyomino tile. In this slide, the bunny region is exactly covered by tetrominoes. Then, we construct a tile graph based on the base tiling. We regard each tile as a node, and we connect a pair of nodes using an edge when the two nodes are adjacent. Our graph partitioning algorithm works on the tile graph. We propose capacity constraint graph partitioning, or CCGP, to decompose the target region into a set of polyomino-like shapes. The CCGP is a variant of CCVT, capacity constraint Voronoi tessellation, proposed by Balzer et al. In 2009. While the original CCVT works on a discrete domain such as composed by pixels or regular grid, our CCGP works on a graph. Also, the original CCVT employs the Euclidean distance metric as in their algorithm. We applied the Dijkstra algorithm for computing distance between nodes. The first step of the CCGP algorithm is to randomly assign partition IDs to each node. The large circles represent the cluster centers. Then, we iteratively swap the assignment until converged. When all nodes are assigned to its nearest cluster centers, we stop the site swapping. Since the CCGP can be performed interactively, users can explore their preferable partitioning by moving the cluster centers. We can generate various shapes of puzzle pieces from a single target shape using this algorithm. Further, by pre-computing all pairwise distances, we can edit puzzle designs with more pieces, as well as puzzle design with few pieces. In this third example, we have 161 base tiles, and thus we can decompose the sword from a few pieces up to 161 pieces. Interestingly, by changing the base tile set, we can also generate characteristic puzzle pieces. So, in this example, we use tetromino base tile set for generating puzzles using the heart as the target shape. But if we change the base tile set, we can generate the other puzzle decomposition with different characteristics. This second puzzle comprises with more intricate piece shapes compared to the first heart puzzle. In addition, we can prioritize base tiles. In these three examples, the I-shaped base tile has higher weights, and when computing base tiling, these tiles are used on a priority basis. Exploiting this weighting scheme, we can also generate partitioning with different characteristics, as shown on the slide. Now we demonstrate our tool. This demo movie demonstrates the puzzle design process. Although we play this demo movie with doubled speed, we edited puzzle piece generation in real time. The user can change the number of pieces and different base tilings to explore piece shape variations. We can extend the CCGP algorithm works on 3D voxel models. In such cases, we use polycubes as the base tile set instead of polyominoes. We can generate 3D polycube or polyomino puzzles. It is not easy for novice users to design 3D voxel models. So, we can create voxel models using Magica Voxel, a sophisticated voxel art editor, and import the vox file into our tool. We compute polycube tiling and CCGP for the given voxel model. Then, we can get puzzle pieces as the partitioning result. During the piece shape generation, we check whether the pieces can be assembled and disassembled successfully. We also get the sequence of puzzle disassembly. This can be a solution for solving the designed puzzle. In this demo, we generate a 4-piece castle puzzle. It takes for a few time to find a valid assemble and disassemble puzzle. Several 2D polyomino puzzle design examples are shown in the slide. In these examples, we use pixel arts as references when designing target regions. We also designed 3D polygroup puzzles. These pyramid and bunny models are partitioned into a different number of pieces. We also exported the designed puzzles and fabricated using a laser cutter and a 3D printer. Although these puzzles are composed of a few pieces, it is moderately difficult to solve for me or for us. In other words, we can enjoy solving our original puzzles. We asked two users, P1 and P2, to design puzzles from a reference pixel art. We asked these users to design puzzles that are hard to solve. We found that while P1 designed the pieces with complex boundary shapes, P2 designed the pieces with different characteristics from P1. P2 thought of hard-to-solve puzzles as puzzles of which each puzzle piece has few clues, hint where to put the piece. That is, P2 avoided complex boundaries. One of the advantages of using our design tool is to be able to design such a variety of puzzle pieces interactively. As the limitations and future work, our 3D puzzle design is still inefficient because we employ stochastic search when finding valid puzzle decompositions. In addition, it is difficult to interact with the 3D puzzle generation process. This is because we have to consider both user controllability and the assemblability of the generated puzzle pieces. Moreover, although we asked two users for our user study, a more dedicated and comprehensive user study has to be conducted for quantitative and qualitative analysis of the proposal too. Conclusion. We have proposed the computational design tool for polyomino puzzles. In contrast to previous work, our tool aims for an interactive design system. Users can edit a variety of puzzle piece shapes. This is achieved by the capacity-constraint graph partitioning algorithm we proposed. Applications include 2D polyomino and 3D polygroup puzzles. That's all. Thank you for listening.